like pat your head or something like that. Okay, so glucose, 6-carbon sugar. It breaks down into 2 pyruvates, which both have 3 carbons. What are the 3-carbon sugars called? Using the same kind of analogy, it's an ose. What do we usually use 3 for? What is our prefix? Triose. Okay, what else do we get out of glycolysis? Overall, we get a net of 2 ATP. That's good. And we also get what? 2 NADH, so 2 reducing equivalents. 2 NADHs. Okay, so that was glycolysis. How many reactions did we have that took us from glucose to our 2 pyruvates? There was 10 overall reactions of glycolysis. So 10 reactions, 10 separate enzymes. There were 2 essential phases that we divided this into. Okay, so the first phase we called phase 1. We termed this the energy investment phase. Okay, so phase 1 is the first 5 reactions. It is the energy investment phase. How much energy do we invest in this phase number 1? 2 ATP, right? So we hydrolyze 2 ATP. So we use 2 ATP in this first phase. All right, so first 5 reactions, we utilize 2 ATP. Then we come to phase 2, where through the art of chemical magic, we essentially isomerize our really low energy potential compounds and make very high potential energy compounds, right? This is what we call the energy output or energy generation phase, okay? What do we get out in these last 5 reactions of glycolysis? We get total 4 ATP, and we get also, very important, the 2 NADHs, our reducing equivalents that we will use later on, okay? So overall, because of that, we have a net of 2 ATP. All right, so what happened to pyruvate? There is a fate for pyruvate. What does it depend on? Right, the presence or absence of oxygen, right? So if oxygen is present, we can imagine if oxygen is present, what happens to our pyruvates usually? So our pyruvates will be going down what we're going to call the citric acid cycle, so we'll call this the TCA. Most importantly, what else happens though? All of those NADHs, all of those reducing equivalents, where do they go? The electron transport chain. So if oxygen is present, oxygen is going to be our terminal reductant or terminal oxidant in the electron transport chain. Those NADHs are going to go there. They're going to give up those electrons to reduce oxygen, and we're going to get a lot of energy generated in the form of ATP out of that, okay? All right, so we're not there yet, though. We don't have oxygen around. So if oxygen is not present, so no oxygen, what happens? So there's 2 different processes with respect to fermentation, right? And it depends on the organism that we're looking at. What happens in eukaryotes? What type of fermentation process do we undergo? Lactic acid. So homolactic acid fermentation. So homolactic fermentation. And what's the purpose of this? Number 1, right? If we don't have any oxygen, that's the whole purpose of this guy. If we have oxygen, this can go off. It can give its electrons to the electron transport chain and be reoxidized so that it can be further utilized in glycolysis. If we don't have oxygen around, how are we going to get this NADH back? That's kind of the purpose of the fates of pyruvate, okay? So this first one, we have homolactic acid fermentation. We take our pyruvate, and this should look really familiar to you guys. We're going to take our reduced NADH, and we're going to reduce pyruvate to what? Should look really familiar. Lactate, right? So lactate is one of our products, and then we also get reoxidized NAD+, okay? So this is what happens in this Homolactic fermentation. Why should this look familiar to most of you guys? What have we been doing in the lab the entire semester? The reverse of this reaction, right? We've been taking lactate, and we've been essentially reducing NAD plus with the lactate, okay? So then, what enzyme catalyzes this reaction? LDH, right? So lactate dehydrogenase, okay? So this is what happens in eukaryotes if oxygen is scarce. Eukaryotes, as well as lactic acid bacteria. Okay, so then one other fate of pyruvate, again, if we're not in eukaryotes and we're not in lactic acid bacteria, what is the other possible fate of pyruvate? Alcoholic fermentation, right? So we have alcoholic fermentation. If I could spell alcohol. What happens in alcohol fermentation? We take pyruvate, and what is the final end product of pyruvate? Ethanol, right? But how many steps does that take to get there? So it's going to be two different steps. We have our pyruvate. And the first step is going to be converted to something. This is also one of the metabolites that cause really bad hangovers. So pyruvate is first converted to acetaldehyde, okay? This is done via the enzyme pyruvate decarboxylase. So it's a decarboxylation reaction. Again, pyruvate was a 3-carbon sugar. Acetaldehyde is only a 2-carbon sugar. So we have decarboxylated it, taken off a carboxylate group. Then acetaldehyde is going to be what? Now again, we have to regenerate our NAD plus from before, right? So we're going to utilize NADH. We're utilizing NADH, forming NAD plus. What is happening to acetaldehyde? It is being reduced, right? So it is going to be reduced to ethanol. And that makes sense because acetaldehyde is a carboxylic acid, or it's an aldehyde, it's not a carboxylic acid, but it has a carbonyl group. That carbonyl group turns into an alcohol, which indicates that it has been reduced. What is the enzyme responsible for this one? Alcohol dehydrogenase, right? So again, this is happening mainly with respect to yeast and various other microorganisms. Do we have an alcohol dehydrogenase in our body? We do, right? We do have an alcohol dehydrogenase in our body. What is it used for? Are we going in the forward direction where we're taking pyruvate and we're forming ethanol in our body? Or maybe doing it in the reverse, right? So alcohol dehydrogenase is present in mammals. It usually functions in the reverse reaction where we take ethanol that gets in there somehow and we take it back to acetaldehyde, which again is why we get such bad effects from hangovers. Okay, all right. Also note what happens. If we do this reaction in the reverse, so this guy is ethanol here. If we do this reaction in the reverse, what are we also depleting? NAD plus, right? So if we do this reaction in the reverse, which we do quite a bit, we also will deplete our NAD plus. What is that going to kind of hinder long term? Glycolysis, right? So if we don't have a lot of NAD plus, that means that we can't generate any type of energy from glycolysis because it's very central to that. What happens if you were to consume too much alcohol? What do you feel like the next day? Very tired, right? That's one big reason why, because you're depleting your NAD plus because, again, this reaction is catalyzing the reverse reaction via this enzyme alcohol dehydrogenase. Okay, all right, so a couple things to note, maybe that you didn't get to. So I'm just reminding you guys where we are. Okay, so let's talk really quickly about energy efficiency with respect to these two possible prospects for pyruvate, okay, both the homolactic fermentation as well as the alcohol fermentation. So overall, with respect to the homolactic fermentation, we are going to take glucose and we are going to turn it in to 2-lactate and then 2 protons. Overall, the delta G for this reaction, I'm going to write all of these in kilojoules per mole, ends up being about minus 196 kilojoules per mole. Okay, so this again is what happens in homolactic fermentation. Okay, so then same thing for alcohol. Alcohol fermentation, we're going to take our glucose and we're going to turn this into, what do we turn it into? Alcohol fermentation, we take our glucose long term, we turn it into 2 ethanols. And then to keep track of our carbons, where do the extra 2 carbons go? So if we go back up to our little homolactic fermentation, or alcohol fermentation, pardon me, this took place in 2 separate steps, right? We had pyruvate, and then what did we do to it? We decarboxylated it, right? So what do we do when we decarboxylate something? We're going to take out a minus CO2, okay? So those other 2 carbons come in the form of CO2 in alcohol fermentation. And overall, for this reaction, we have a Gibbs free energy value of a minus 235 kilojoules per mole, okay? Okay, so that's how much energy, in theory, if we take glucose and we produce these 2 products, we could generate, right? What do we actually end up doing with most of that energy? So we do make 2 ATPs from it, right? So the synthesis of ATP comes from ADP and inorganic phosphate. That gives us our 2 ATP. How much do you think this costs with respect to energies? Two ATP. How much do you think it costs? Each one costs about 30 kilojoules. Okay, so if 1 ATP costs 30 kilojoules, how much are 2 ATP going to cost? 60, right? So this reaction overall will be about a positive 60 kilojoules. Okay, so now both of these processes could, in theory, generate around 200 kilojoules of energy. We only utilize them to use 60 kilojoules of that, right? So the overall efficiency of both of these processes is very low. For lactic acid fermentation, this ends up being about a 30% efficiency. And for this guy, our alcohol fermentation, that ends up being about 26% efficient, okay? Right, so what's the problem with that? Where does the rest of the energy go? Heat, right? So the majority of the time, with pretty much 70% of the possible energy, or Gibbs free energy, that could be formed from both of these processes, the majority of it is just dissipated as heat. What does that make these, though? It's kind of the important point of this. It makes these reactions irreversible, okay? So they occur, and they're irreversible, and they cannot go into reverse, okay? And because a lot of that is the dissipation of heat, or of energy, as in the form of heat. So, if we look at both of these processes, no oxygen present, both lactic acid and alcohol fermentation, they waste a bunch of energy, right? What is the benefit of them overall, comparatively to some sort of oxidative process where we actually utilize an electron transport chain, we have TCA cycle, etc. What is the benefit of just doing glycolysis and doing fermentation? It's super fast, right? So glycolysis is about 100 times faster than any type of oxidative process. Oxidative process. So it's profligate with respect to ATP. It wastes a lot of energy, right? But it is fast. And so that is the benefit overall of undergoing this glycolysis to fermentation type process, okay? Okay, so again, reminding you guys, ideally where you think you got to last time, okay? All right, so now we're going to go back to glycolysis. We're going to go back to a couple of the key concepts that we may have missed out on in the first go-round of this. Skip the slide. Regulation of glycolysis. How do we regulate glycolysis, right? So long term, again, we have glucose, and it goes to pyruvate, and it does so in 10 steps. We are doing this, or we are not oxidizing, but we are taking glucose, breaking it down to pyruvate to form ATP. What if we don't need ATP? We need a means by which we can turn this off, right? And so that's what we're going to talk about. How do we regulate glycolysis? How do we turn it off when we need to turn some other type of process on, etc. Okay? So there are going to be two different types of reactions that we're going to look at with respect to glycolysis. They're going to be reactions that we call near equilibrium versus far from equilibrium reactions. Did you guys talk about this at all? No. Okay, so near equilibrium reactions. These guys are going to have delta G's that are approximately 0, right? If we're at equilibrium, what is delta G? 0. So at equilibrium, delta G is 0. So for the majority of these reactions, these are going to be near equilibrium reactions. They're not going to be quite at 0, but they're going to be very, very, very close. The important point behind that, with respect to these near equilibrium reactions, is that they are going to be reversible. What does reversibility tell us about an enzyme? It can go in the forward direction, right? But can it also go in the reverse direction? Yes, it can. What's going to depend on whether or not it's going forward or whether or not it's going in reverse? It's going to be able to shift which direction it goes based on what? Concentration, right? So both of these guys, or all of them that are these near equilibrium reactions, are reversible, meaning it can shift direction based on concentration. So concentration of the reactants and products alone. Okay, so then those are near equilibrium reactions. There are also going to be reactions that are far from equilibrium. So far from equilibrium reactions are going to have delta G's that are negative and large. So very negative and large gives free energies. Now, what is that going to tell us about the reversibility of these reactions? If this guy is negative and large, that tells us that these reactions are essentially irreversible. Okay? So because of that, do you think that we can control the forward and reverse process, or control the rate of the forward and reverse process based on concentrations? No, right? And so these far from equilibrium reactions, we essentially cannot control based on concentrations. What other means do we have by which we can control the rates of reactions? Allosteric, right? So allosteric interactions, right? Allosteric effectors, inhibitors, stuff like that. So one way that we're going to be able to control these is allosteric effects. What happened in allosteric effects? What does an allosteric effector do? Right, so it binds to some other region other than the substrate binding site in the enzyme, and it changes the structural conformation, right, to either turn the enzyme on or off based on whatever it's actually doing. So allosteric effects are going to be one way that we can control these. Number two is going to be covalent modification. And I haven't talked about this, but we will talk about this at the end of the chapter. Okay, this is going to come back to actually hormonal control and types of signaling pathways that we haven't discussed. Okay, all right, so what's the purpose of all this idea behind near equilibrium and far from equilibrium reactions, right? So ideally what we're going to be trying to control is the rate of flux to which metabolites move through these pathways, right? If we want to slow a pathway down, we need a means by which we can slow down the flux of metabolites. That's what we call this overall rate of reaction, the flux of metabolites through a system. If we want a means by which we can speed it up, we need a means by which we can speed up the flux of metabolites through a system. And so the reactions that we're going to be able to do that with are not going to be the near equilibrium reactions. They're instead going to be the far from equilibrium reactions. Okay? So if we go back to glycolysis, I'm going to zoom in here. And we compare the Gibbs free energies for the 10 reactions of glycolysis. So note right here that I have delta G naught. What is delta G naught telling me, or delta G naught prime? We're at biochemical standard state, right? So for the reactions that are actually occurring in the cell, are they going to be a biochemical standard state? No. So instead, what's most important is delta G by itself. So these are essentially going to be trying to show the actual free energies available for the reactions with the concentrations of reactants and products as you would find in vivo, okay? All right, so as we look at these guys, ideally a few should stand out. So anything that's close to 0 is a near equilibrium reaction. Anything that has a negative and large delta G is going to be a far from equilibrium reaction. So what is one of these if we're looking at our delta Gs? So I want a far from equilibrium reaction. For the first one, hexokinase is a far from equilibrium reaction. We have a minus 27 kilojoules per mole. What's another one that's far from equilibrium? PFK, phosphofructokinase. So that's another big one. And then there's one more that's important. PK. What does PK stand for? Pyruvate kinase, okay? So pyruvate kinase is that last one. Okay, so we have 3 possible ways that we're actually going to be able to control the flux of metabolites through glycolysis. It's either going to be hexokinase, phosphofructokinase, or pyruvate kinase, okay? So for hexokinase, what does hexokinase do? We take glucose, and what does it do to glucose? It phosphorylates it where? 6-carbon, right? So we get glucose, 6-phosphate as a result. That's what hexokinase does. What does phosphofructokinase do? PFK, very big important enzyme. It takes fructose 6-phosphate. What does it do to it? It's a kinase. Kinases do what? They hydrolyze something and they add stuff usually. So kinases hydrolyze ATP. If it's hydrolyzing ATP, what is it probably doing to fructose 6-phosphate? Probably adding a phosphate group to it. Okay, so what we come out of here is fructose bisphosphate. So this is fructose 1,6-bisphosphate. Okay, that's what phosphofructokinase does. PFK. And then the last one, this guy, pyruvate kinase. Pyruvate kinase takes PEP, phosphoenolpyruvate, and turns it into what? Pyruvate. It is the last little step in glycolysis. So this is what pyruvate kinase does, okay? Now, if we're trying to consider which one of these is going to be the major flux controlling enzyme, how beneficial would it be to have that last step in the reaction be the way that we control the overall flux of metabolites through the system? So if we took pyruvate kinase, or maybe do 3, this is our third one, and we said, okay, we're going to regulate flux of everything through glycolysis by regulating this last enzyme. How efficient would that be? Not very efficient, right? So it would be wasteful to wait to the end to try to regulate the flux through metabolite or through glycolysis. What about the first one? Glucose going to glucose 6-phosphate. That would be smart, right? That would be like a first concomitant step in a pathway. But the problem with the first reaction is that there are other ways to get into glycolysis besides going through this first step. So other sugars can get into glycolysis bypassing this original step. Okay, so we can't regulate the flux of metabolites through glycolysis here. So the thing that we're going to focus on, and the one that actually helps regulate the flux of metabolites through glycolysis, is PFK. It's high enough on the reaction pathway, but again, it's going to be past a point where we've had some sort of concomitant steps. We can't get in after what happens with respect to PFK. Okay, so that's going to be PFK. Phosphofructokinase is going to be the way by which the cell regulates the flux of metabolites through glycolysis. So what are the various things that are actually going to affect this? So you guys talked about PFK? A little bit, right? So, okay. So, PFK, it's beautiful. It's this beautiful little enzyme, right? It has two separate sites that are important with respect to the enzyme. This is a dimer. We should probably state that. So this is a dimer, right? We have two separate subunits that do the exact same thing. There are two important sites in PFK. There is this site, which is the substrate binding site. So substrate binding site. And then there's a separate site down here, which is where our allosteric effectors are going to go. So this is our allosteric site. Okay, so now consider the reaction that PFK catalyzes. Who are the substrates? So substrates, number one, is fructose 6-phosphate. But what does phosphofructokinase do to fructose 6-phosphate? It adds a what? Phosphate group. So what is going to be another co-substrate in this reaction? ATP. Okay? So there are two substrates, ATP as well as fructose 6-phosphate. And they both go into the substrate binding site. Okay? Now, there is going to be a couple of allosteric effectors. So the first allosteric effector, which we're going to call an allosteric inhibitor, is also ATP. Okay, so ATP is an allosteric inhibitor and can also bind at this allosteric site. So there are two places where ATP can bind to this enzyme. Okay. Phosphofructokinase also has allosteric, what are they called? Activators, right? Something like that. Something that speeds up its overall reaction rate. So there's a word for this, and I'm just blanking entirely. Inhibitors versus nobody? Nothing? Activators? Am I right on that? I would have written it down somewhere. Okay, so we'll call it an activator. I don't know if it's called an activator. But again, it's going to be something that binds and actually speeds up the overall reaction rate. Okay? So the allosteric activators are AMP and ADP, as well as, no, that's it, AMP and ADP. Okay. Yeah, okay, all right, so we're going to focus on these two. We have an inhibitor versus an activator, right? And so when we talk about these allosteric enzymes, we have two different ways to describe them, right? We talked about it with respect to hemoglobin. What is the more active version? What did we call hemoglobin in the more active version? It was like a letter. It's not like a big name or anything. We had R versus T, right? So R versus T. And which one was the more active version? R, right? So this stood for relaxed. Regardless of what that means with respect to hemoglobin, we keep the exact same definitions and connotations with respect to all of the allosteric enzymes. So R is the more active version. And then T, we call this tense. This is the less active version. With respect to hemoglobin, we talked about binding, but with respect to phosphofructokinase, what are we going to be looking at with respect to more active versus less active? We're going to be looking at activity, right? Because this is an enzyme. It's actually doing a reaction. It's catalyzing something, okay? So now, oh yeah, activated. There it says. Okay. Anyway, all right, so let's look at the actual phosphofructokinase activity in the presence and absence of some of these inhibitors and activators. Okay, so again, ATP is an inhibitor. So if we sit here and we look at this little activity plot as a function of substrate concentration, we are at about 100% activity at 0.5 millimolar F6P, fructose 6-phosphate concentration. Okay, so in the absence of everything, very active at this concentration. If we add 1 millimolar of ATP, what happens to the overall concentration at this 0.5 millimolar, the overall activity at this 0.5 millimolar concentration? It decreases a lot, right? So this ends up being about 15%. So that shows you that the presence of ATP dramatically inhibits this reaction, okay? Now, if we take the same exact thing and we add just a little bit of AMP, which is an activator, what happens to the activity of this enzyme? It increases quite dramatically, right? So we end up being about 50%, okay? So this is the big idea. ATP is the final end result of this pathway, right? If we have a lot of ATP, do we need more glycolysis? No. So ATP, by coming back to phosphofructokinase and binding the allosteric site, turns it off, so we decrease the rate of flux through glycolysis, right? So one thing to note is that the concentration of ATP overall actually doesn't change that much, right? Even when we are completely depleted of ATP, we still have a gigantic amount of ATP present. The thing that really does change, though, is the AMP and the ADP. So if we're continuously hydrolyzing ATP, our products are ADP and AMP. If those concentrations increase, then these guys come in, they outcompete ATP at this binding site, and they increase the activity overall, okay? So the real effectors here are the AMP and the ADP. As they increase in concentration, we need to turn PFK back on. We need to increase the rate of flux of these metabolites through glycolysis, and so that's exactly what they do, okay? Okay, all right. Jeez, I thought I'd get farther. All right, okay. So this one's a big one. We're going to come back to this guy because there's also going to be a competing pathway that we're going to have to deal with, and we need to be able to control him, PFK, as well as the enzyme that catalyzes the opposite of PFK in the reverse reaction. So we're going to come back to PFK at the end when we talk about regulation. Okay, so last little bit of this slideshow at least. Other sugars, right? Other sugars besides glucose and how they get into glycolysis, okay? Okay, so what type of sugar is a glucose again? It's a hexose, it's a 6-carbon sugar. If I actually draw glucose, which I probably shouldn't do, that's usually flirting with disaster. So if I draw it in the linear form, carbon, 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 1, 2, 3, 4, 5, 6, H2, OH, and then we get OH, 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 I think. Yes, good. Wait, no, nope, wrong. OH, OH, H, 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 H. This is D-glucose. This is what we deal with, okay? Why would I draw this? What's the purpose of me showing you this? That's it. That's great. So this is D-glucose. Super happy about that. What type of carbonyl group does it have, though? This is kind of the purpose of this. What is this group called up here? This is an aldehyde, right? So this carbonyl for glucose is an aldehyde. So because of that, glucose is what we call an aldose, okay? Because it is an aldehyde sugar. It has an aldehyde group. That's where the carbonyl is at. All aldoses have an aldehyde group, okay? There is another form of sugars, though, and they're called ketose, right? So what do you think ketoses have? A ketone, right? So they have a ketone group instead, okay? So there are going to be 3 different sugars that we talk about comparatively to glucose. We're going to talk about fructose, we're going to talk about galactose, and mannose. We're going to talk about how they get into glycolysis if we don't actually have glucose around. So in comparing fructose to glucose, fructose is a ketose. It is a ketone sugar. This guy is a ketose. And I should probably state that down here. So fructose versus glucose, these guys are ketose versus aldose. Galactose and mannose, on the other hand, are both aldoses. They're both aldehyde sugars. Okay, so a ketone versus an aldehyde, if everything else is the same, what are they called? Can we go between a ketone and an aldehyde? Is there a way to get between one versus the other? What is that reaction called? Going between a ketone and an aldehyde. It's a tautomerization reaction, right? So fructose and glucose are both tautomers of one another. Tautomers, right? Okay, so then between glucose, galactose, and mannose, these guys are all aldose sugars, so there's not tautomers of one another. Instead, they're called epimers. So does anyone know what an epimer is? The only way epimers differ from one another is configuration at one of the carbons. Okay, so epimers differ in configuration at 1 carbon. So when we compare glucose versus galactose, that 1 carbon ends up being carbon 4. So these guys just differ in configuration about carbon 4 versus glucose versus mannose. This guy, they differ in configuration about carbon 2. Okay, so now, that's the difference. Definition of an epimer versus a tautomer, ketose versus an aldose. Now, how do these guys actually get into glycolysis? We're going to start with fructose, and fructose is kind of the most interesting one of the bunch. Okay, so fructose, again, ketose sugar. There are 2 separate pathways by which fructose gets into glycolysis, okay? So fructose in the muscle can be directly converted to fructose 6-phosphate by hexokinase. Why is that? What does hexokinase normally do? Right, so hexokinase transfers a phosphate group to glucose. That was the original enzyme, the original step in glycolysis. What was the big thing about hexokinase, though? It's very nonspecific. Okay, so hexokinase in the muscle is extremely nonspecific. It acts on most 6-carbon sugars, and so because of that, fructose is a 6-carbon sugar. It can also phosphorylate fructose to fructose 6-phosphate. Now, that's not that interesting. What's more interesting is what happens in the liver. Okay, so in the liver, with respect to fructose, there is no hexokinase. Okay, and so the initial step in the liver uses a different enzyme, and so because of that, fructose cannot be directly phosphorylated to fructose 6-phosphate. Instead, what happens is an enzyme called fructokinase phosphorylates it at the 1 position, and we get fructose 1-phosphate. Okay, so now what happens to fructose 1-phosphate? There is no enzyme that can directly convert this into fructose 1,6-bisphosphate, which would be great if there was, but there isn't. So instead what happens is that a aldol cleavage reaction occurs. So it takes this fructose 1-phosphate and it cleaves it. Have we seen that before? An aldol cleavage reaction, you take a 6-carbon sugar and you cleave it to make 2 3-carbon fragments. Yes, so what reaction would this kind of be similar to? That's in glycolysis already. So if we took our fructose 1,6-phosphate, this is also fructose bisphosphate, and we react it with an enzyme. It's called an aldolase. What do we make in glycolysis? Right, so we get glyceraldehyde 3-phosphate, and we get dihydroxyacetone phosphate. Between these two, which one continues on throughout glycolysis? GAP, right? So there's another enzyme that converts glyceraldehyde or dihydroxyacetone phosphate into GAP. So that's going to be what happens with respect to fructose. We're going to cleave it, but instead of getting glyceraldehyde 3-phosphate and dihydroxyacetone phosphate, we're going to get just glyceraldehyde. Need my highlighter. And then we're also going to get dihydroxyacetone phosphate. Okay, that's fine, right? Dihydroxyacetone phosphate, we have an enzyme that converts it into glyceraldehyde 3-phosphate, which will continue on. That enzyme is called what? Because we also see this enzyme in glycolysis. DAP going to GAP is catalyzed by this triose phosphate isomerase. We abbreviate this guy TIM, right? Also, glyceraldehyde can be directly converted to GAP as well, which will go on through glycolysis by direct ATP or direct phosphorylation. It can also undergo 3 reactions that will convert it to dihydroxyacetone phosphate. Okay, that's great. Lots of different ways by which it gets to GAP. GAP then goes on through glycolysis. Okay, so now, what is the problem with this? fructose in the liver, right? Where does it enter glycolysis as? So we did all of these various things. It enters glycolysis as glyceraldehyde 3-phosphate. What's the problem with that if we're trying to regulate the rate of metabolite flux through glycolysis? Who do we bypass entirely? PFK, right? So fructose in the liver gets converted directly to glyceraldehyde 3-phosphate, which completely bypasses the one control point of the rate of flux of metabolites through glycolysis, right? This bypasses PFK. What's the problem with that? If we don't need ATP and you have fructose in your liver, does it care? No, right? It's still going to get through, produce lots and lots of ATP. What's the problem with that? So we're not turning off something that we don't need. We're not turning off something that's going to make metabolites that are just going to essentially accumulate and go on to make fatty acids, okay? So this continues on, unchecked, unabashed, right? Long term, all of these metabolites, all this ATP builds up, and they move into making fatty acids. What's the problem with that? If you're a mammal living in 2018 and trying to watch your weight. Right. So this is the problem with fructose, right? In the liver, because it goes unchecked, because it essentially completely bypasses our one big control point, all it does is sit there and get metabolized and turn into fatty acids, right? What does that lead to long term? Obesity, long term, right? So this is why people think that the high fructose corn syrup diet that we continue to consume is leading overall to this increase in obesity with respect to the modern American person, because fructose is unchecked in the liver. It's not unchecked in other areas of the body, so don't think that if you eat a bunch of fruit you're going to get fat, because that's not the case. But again, it's going from high fructose corn syrup. Where do you guys usually get that from? Drinks, soda, right? High fructose corn syrup goes into all of our various beverages that we drink, etc. Okay, so that's a problem. Oh no. Does it think that I'm not here? I'm here. Hi. Oh, forget it. I'm pissed. Okay, so that's a problem, right? And so that is the problem for fructose with respect to what happens to its metabolism in the liver. Okay, so let me unplug, plug back in. There we go. Yay, okay, all right. There's only 2 more sugars that I'll bother you with, okay? Okay, so fructose, big issue. And then we continue on through glycolysis as just glyceraldehyde 3-phosphate.
But more of it is stored as fatty acids.
Yeah, so long term, if we keep doing that, we're going to get a bunch of pyruvate built up, we're going to get a bunch of ATP built up, and that's just going to be converted directly into fatty acids. Okay, so don't drink sugary, syrupy sodas. They're bad for you.
So is that the end of it? It just doesn't go...
It goes into glycolysis as GAP. Couple more sugars. Galactose. What happens to galactose? How does galactose get into glycolysis? So it's important to note, where does galactose come from? So lactose is a disaccharide that consists of both galactose and glucose, right? So where do we get lactose from? Dairy, right? Any type of weird dairy that we're not supposed to consume. Okay, so that's where galactose is coming from. It's from this disaccharide lactose, which is coming from the dairy that we consume in our diet. Again, what's the difference between galactose and glucose? They are epimers, right? And so if we number these carbons, this is 1, 2, 3, 4, 5, 6. These guys differ about their configuration at carbon 4. Okay, so they're epimers of one another. Unfortunately, hexokinase, while it is super nonspecific, cannot utilize galactose and phosphorylate it directly. Right? So instead, we have to undergo an this reaction, not even try, epimerization. There we go. Okay, epimerization reaction to get our little galactose to glucose before we can start on into glycolysis. Okay, so how do we actually do that? So super drawn out little thing. Big important thing to note here is that the first step that occurs in this cycle, galactose, is going to be phosphorylated, but it's going to be phosphorylated at the carbon 1 position to make galactose 1-phosphate. This is going to be catalyzed by this enzyme galactokinase. Okay, so again, long term, it wants to get to glucose 6-phosphate. Before it can do that, it has to be epimerized to glucose 1-phosphate. The thing that does that is this little uridine derivative. Okay, so this is going to utilize a cofactor that's called UDP glucose. This is a UDP molecule, uridine diphosphate attached to a glucose. What happens is, this UDP glucose transfers its UDP little functional group to galactose. It's going to get off, or the glucose at that point in time is going to pop off as glucose 1-phosphate. That continues on. It gets isomerized by phosphoglucomutase. That becomes glucose 6-phosphate. The epimerization reaction is what occurs after. So we're left with UDP galactose. That is going to be epimerized in a second reaction that turns it into glucose. And it's just going to continue and continue and continue. Yes?
Where's UDP?
UDP, I don't know, metabolites in the cell. We don't ever really get into nucleic acid synthesis, so it's hanging around. There are a lot of these little things that just kind of come and appear out of nowhere. Magic, Deus ex machina. Okay, so UDP glucose gets epimerized. No, UDP galactose gets epimerized via this little enzyme. It requires NAD as a substrate, but it does not reduce or overall oxidize NAD, so they think there's some sort of reaction where NAD gets reduced, but then it gets reoxidized in the same exact catalytic cycle to give us our UDP glucose, which we continue on with, okay? So how does galactose get in? This little pathway, which essentially goes from galactose 1-phosphate to glucose 1-phosphate, which is then isomerized to glucose 6-phosphate. That moves on to glycolysis. Okay, one more. Mannose. Mannose is also an epimer of glucose. It differs not at the 4-carbon, but instead it differs at the 2-carbon. So mannose has a different configuration than glucose does at this position. Guess what's great about mannose, though? With respect to not being bored, with respect to how sugars get into glycolysis, mannose is recognized by hexokinase, right? So how does mannose get in to glycolysis? It gets phosphorylated by our little non-specific hexokinase. We get mannose 6-phosphate. That is then isomerized via phosphomannose isomerase to give us our fructose 6-phosphate. Okay, so no big UDP things with respect to that one, or 7 different reactions to get you to glyceraldehyde 3-phosphate. Instead, you just get there the hexokinase and an isomerase. Okay, so that is the end of this section. And I'm going to go ahead and end today with that, because